Okay, welcome to the review session for the second midterm. The uh, rules are the same as previous time, closed book, closed notes, but a one-page equation sheet, double-sided, pencil, pen, and calculator. 90-minute test for which you're able to stay for 4 hours. And this particular second midterm covers the material between weeks 4 and 7. So fluid dynamics was Bernoulli in weeks 4 and 5, conservation of mass and moving control volumes in week 6, and conservation of momentum in week 7. Specifically for the scheduled exam, the 3 questions, each with equal weight, 110 points, full score is 100 points. Are from Bernoulli along streamlines, which is really chapters 4 and 5, and free jets, which is part of Bernoulli as well. Conservation of linear momentum and conservation of mass, and again Bernoulli along streamlines, free jets, and manometry, which is from the earlier stages, but actually manometry is really linked to Bernoulli's equation. So those are 3 equations or 3 questions for the scheduled midterm. Again, the best way to review this material is to look at past exams. There are only a finite number of questions I can imagine asking, and so previous exams over 10 years should give you a reasonable broad scope of exactly what the potentials would be, but they are limited to these 3 areas for the scheduled exam. Okay, so first, Bernoulli. We know that Bernoulli equations are written along a streamline. They're defined in terms of an upstream and a downstream location. When we're not worried about loss of energy in the system, we can have either one as upstream or downstream. It relates to a streamline velocity between the upstream and downstream locations, maybe a cross-sectional area, the density of the fluid, and I guess at each location, a pressure at those locations and an elevation at those locations. And based on that, and for our coordinate system, which is really along the streamline, but the z coordinate system matters, which is positive upwards. And that allows us to write Bernoulli equation in terms of upstream as an elevation plus a pressure head plus a velocity, an inertial term, v1 squared over 2g, and that's equal to the downstream components of that in terms of pressure and elevation, pressure, and velocity head. These are always streamline velocities. These are always elevations relative to positive upwards in terms of the sign convention. And we have to be able to define which one of these, for this to solve this equation, which one of these we don't know and can therefore solve for if we have all 5 other components which have to be known. If we only have 4 known values, we have to constrain it some other way, and that constraint is usually conservation of mass, which is just that the upstream area, its velocity and density is equal to the downstream area, its velocity and density. These have to be the same, so these cross out. And conservation of mass allows you to be able to solve for you only have 4 known values because you're really constraining it in an extra separate way. So that applies within the flow field. We know that we can use this to calculate behavior of free jets. We know that if we have velocities, then we can look at solving along a streamline for the behavior that we would have if things are airborne. The requirements are that if we know the exiting velocities guess Vz in this particular case, right? Vz and Vx. We always have Bernoulli's equation defined in terms of a streamline velocity. And so we know that velocity in the x direction would stay constant as long as nothing acts on the fluid, and therefore we can arc a streamline to be able to look at that particular behavior for an airborne jet, if it were per se. Okay. So in manometry, I guess, we know that if we have a fluid in a bucket, and we have fluids at two particular locations, 1 and 2, we can always draw, if it's static, then any streamline can apply, right, between any point, because velocities are 0. And if you write Bernoulli for that particular case where the velocities are 0, then the manometry equations come out, which are just that Z1 plus P1 over gamma is equal to Z2 plus P2 over gamma. And so in that particular case where we define a coordinate system with Z vertically upwards, we can merely rewrite this equation as, for instance, P1 is equal to P2 plus Z2 minus Z1 multiplied by unit weight. And of course this value here is the height separation between these two locations, and is basically the same expression that we've used in manometry. And so you remember in manometry that if you go up, you subtract fluid pressures. If you go down, you add fluid pressures. And the sign of this particular H value you have to apply is just conditioned by this. So manometry is merely just a special case of the Bernoulli equation where the velocities, because it's a static fluid, have to be equal to 0. Okay? So that's what you might need in terms of manometry. In terms of conservation of mass, and so we usually think of that in terms of a control volume, and control volume into which we have fluid traveling, and that fluid goes across both an upstream boundary and a downstream boundary. And if we have locations 1 and 2, then we have velocity into the system, velocity out of the system. It's important for us to define this normal to the boundary on a surface, a control volume and a control surface define the bounds of the system. And in the way that we've talked about it, we have upstream and downstream areas. And for those particular conditions, we can define the conservation equation as a product of density times the rate of change of volume of the system plus the volume times the rate of change of density of the system plus sum of the mass flow rates has to equal 0. Basically, mass rate in equals mass rate out, and if the volume of the control volume changes, or if the density included in a static control volume changes, these represent these rates of change of the product of volume and density. So this is just a differentiation of this particular term. If it's steady state, then these two terms in here are equal to 0, and you're just left with this particular term. These mass flow rates we can always define as being equal to the sum of the velocity times the density times the area. So this is just the mass flow rate is just this term here, multiplied by the area of which it flows is the total amount. And if we happen to have, we can define it both in terms of static and moving control volumes. The control volumes we define are in this generic way that we've talked about a boat moving, where you have, for instance, someone shooting a velocity of fluid off the ship, the boat itself moving at some rate for the velocity of the control surface, and relative to someone who's sitting on the dock, the velocity of the jet coming out of here that's moving on a boat that's moving at this velocity is just given by v static is equal to the velocity of the control surface plus the velocity of the fluid coming out of the hose at the front of this. And so in cases where we have a moving control volume, we can always write the sum of the mass flow rates as being equal to density times the relative velocity times the area, or sum of those, to be able to solve for the fact that the control volume is actually moving. The sign convention is important to be aware of. And so volumes that increase are positive. Densities that increase are also positive. And mass flow rates out are positive. Because the velocity multiplied by the dot product of the velocity and the normal to the boundary are positive on this side. So in terms of mass flow rates, if it's out across the face in this direction, then that's positive. And if it's in to the volume on the back side of this, then it's a negative magnitude. And these are always the summations of those individual components. So the same concepts, they come from Reynolds transport theorem, can be used for conservation of momentum. And for these, again, we have a similar idea that we have a control volume that fluid is going into and across a surface in a downstream location and an upstream location. We have to define a coordinate system which is relevant to our behavior. And again, the unit normals to the boundary. And so for steady systems, we can always define conservation of momentum as a sum of velocities and mass flow rates and equate those to forces that are applied on the system. These are each forces in the x, y, and z directions, but typically we resolve one at a time. And so if we resolve, for instance, in the x direction, then we just use one component. We can also be aware of the fact that we can use the static velocity here to substitute into this. And so the full expression that we might want to use is it's the sum of the velocities of relative to the control surface CS, not SC, multiplied by mass flow rate is equal to the sum of the forces. Again, these are vectors, but if we're doing it just for one direction, I guess this would be for x, y, and z, only one. If we just did it in the x direction, then it would be the sum of x plus mass flow rate. Mass flow rate is always a scalar value, not a vectoral value, and the sum of forces in the x direction. And so we can resolve those. This mass flow rate is always given by the density, the area, and the relative velocity across that surface. But these are separately defined in this particular way to be able to accommodate the fact that the control surface might also be moving at some velocity. And these would be static flow rates. And so we need to be able to make the distinction between relative to the boundary velocities and the velocity of the control surface. And so the sign convention for these, we have two components. We have a sign convention that goes in to define mass flow rates and one that defines velocities. These are always, importantly, relative to the coordinate directions, x, y, or z. Positive relative to these. And so in this particular case, if we are looking at mass flow rates, then because this is out of the volume, then this would be positive. It's in the same direction as the unit normal. And because this is into the volume, this is negative. But for both the velocities of the control surface and the velocities relative to the boundary, these would both be in the coordinate directions, these would both be positive. And so we need to be aware of that difference in sign convention that accommodates that. And so the other place to look for this is, I think, the lecture for 7.3 from 2018 might be worthwhile looking at it, at least the first half before it starts talking about rotational conservation of momentum, conservation of rotational momentum, or angular momentum, is perhaps worth looking at it for the half part because it describes this quite broadly. And that's about it. So those are the main topics that you need to be able to understand. And if you understand the equations that we've just put down here, as long as you know how to use them, then I think you fare well. Okay. Thanks very much. Good luck.